You hear me? Yeah, welcome back, everyone. This is the second instance of Greta Panova's lectures on algebraic combinatorics, and today she's going to talk about Lozenge tilings. Thank you.
Thank you very much. Hello, everyone, again. So today we are going to talk about some research and some general ideas that are behind Lozenge tilings, in particular from the point of view from algebraic combinatorics and symmetric functions, which I was talking about in the previous lecture. So these are, in some sense, the same Lozenge tilings that Rick was talking about, but the tools we are going to use are quite different, and the perspective is quite different. Okay. So what are the tools? So the tools are these Schur functions, the characters of the general linear group, and the generating functions for semi-standard Young tableau and determinantal symmetric functions and so on. So all of them are the Schur functions, and they can be used to analyze a lot of models. You will see why they're so prolific in a moment, but basically today's talk we are going to focus on Lozenge tilings. So this here, and we are going to have two perspectives. So one is the usual Lozenge tilings with uniform weights that you know about. So tilings with this rhombi of the rectangular grid, where we define some domain in this grid, and we look at all possible tilings. For the half of this talk, we're going to be interested in tilings which are uniform. So every tiling has the same weight and is equally likely as any other. And of course, as we mentioned already several times, Lozenge tilings really are a three-dimensional view, and it's also, you can see the height function in here, of a dimer model on the hexagonal grid. So here you can imagine some molecules with such connections. So, and as I showed the previous time, so we can also think of Lozenge tilings and non-intersecting lattice paths, but this is not actually how we are going to treat them in this talk. But this is the original reason why, say, Lozenge tilings of the hexagonal grid were studied more than 20 years ago in the seminal paper of Rick, Canyon prop, and so on. And the non-intersecting lattice paths giving the determinantal structure makes this model integrable and makes it possible to compute correlation kernels and so on. So, but this is going to be more subject of Rick's talk. And for our talk, we are going to look at them from other perspectives. And what kind of problems do we really care about here? So we are in the context of probability right now. So we are going to let the mesh size go to 0. So we are going to look at some region in the plane and look at all possible tilings. They are going to approximate a step surface, and we can start asking many probabilistic questions of how does this surface behave in the limit. So for example, the law of large numbers question, is there a limit shape that Rick was talking about last time? Is there a frozen boundary? So are there some regions where we have probability 1 of seeing only one particular type of lozenge, which for this hexagon is the case. And what do things look like when we zoom near the boundary? What kind of distributions do we have for these lozenges? So today we are going to focus on this here. Well, we'll mention something about the limit shape as well, and see how we can study all of this. So far so good. Everybody hears me, other than okay. All right. And there are different conditions we can impose on these lozenges. So as I said, so the local weights are gonna be uniform, but we can impose some other global conditions. For example, we may want to have them symmetric around the vertical axis. So we may want to tile the hexagon in this case, or we can have them symmetric about some point in the middle. And really, in this case, we really have to look at this as a flat tiling if you want to see the symmetry, because when it's three-dimensional, it's a little bit more difficult. And now we are going to explore probabilistic behavior using algebraic combinatorics tools. So first of all, in order to be able to state the results, we need to parameterize the region somehow. And from the point of view of our methods, it's convenient to parameterize the region as follows. So we have what's called a trapezoidal region. So we have 3 flat sides. And then, so this dimension here is gonna be big N. So if we impose this flatness and we tile the region, you can convince yourself as a combinatorial exercise that when you look at the end vertical line, so this is what I mean by end vertical line, so the one that I just drew over here, we are going to have exactly N, big N, horizontal lozenges which are sticking out. And we can encode their positions with their heights. And when I say height, I mean really the distance, the actual distance from this point to this point on top here. So in this example, the heights are going to be 0. So this is going to be 0, 1. This is not a lozenge. So 1, 2, 3, 4. So here we're gonna have 5 and so on. And because these are increasing numbers, we can subtract 0, 1, 2, 3, 4 from them, and the resulting sequence of lambdas is going to be a partition, an integer partition, our favorite object. And now this is how we are going to encode the region, the 3 flat sides, and the positions of the horizontal lozenges on the right side, given by some partition that has n parts, not necessarily all non-zero. So this is our lambda n, and it doesn't have to be that this lambda n, when rescaled, actually approaches some finite polygon. It can be anything. For example, it can be the staircase. So you cannot. It's not going to give us like something like the hexagon as we may be used to. But just as an exercise, let's see what happens when we have the hexagon. This is the original, the prototype of all of these studies. So the hexagon was the first domain lozenge style domain to be studied. So here it is, this red region, of course. So how can we parameterize such a region using these notions with the lambdas? Well, if we take the horizontal lozenges at the bottom to be one after the other right here, they are basically forcing the entire region over here to be flat. And if we make them one after the other on top, they're also going to force the entire region to be flat, and they're going to cut out exactly this type of boundary. So we are able to use this parameterization and parameterize any finite polygonal domain as well. So this is just an example. Okay, so what kind of questions and results are we looking at here? Probably my favorite in this business is when we take a large lozenge tiling. So this picture is generated by Leonid Petrov, by the way. Sorry. And if let's say we zoom at the border, at the horizontal border. So again, we don't have to deal with the hexagon. It's just that it's one of the best examples. If we zoom at the border, we see that lozenge tilings look like this. So we have one horizontal lozenge right next to the flat border, and then we have two more, so it's always like this, two more horizontal lozenges on the next border. This is how the geometry forces it. And one of them is below and the other one is above the previous one. Sorry, this is not, I cannot erase here. So this is how these conditions look like. And we can ask about the joint distribution of these positions of the horizontal lozenges near the boundary. This is how the heights form these inequalities, these triangular inequalities, and this is what we really would say, how we would say that two partitions interlace, for example. So these are the same conditions. And now the question is, what's the joint distribution of this, the collection of all these numbers over here, as n goes to infinity. So of course we need to rescale somehow, because we are going to have to, they're going to be too large. So we will rescale by, so this is another question, what do we need to rescale by to see actually something interesting? And that was the motivating conjecture, which was, well, there was an argument for it actually. So Kunkov and Rishtikin gave an argument why something like this should be true in a paper from 2006 called The Birth of a Random Matrix. And here is the random matrix. The joint distribution converges to what is called the Gaussian unitary ensemble corners process. Basically, if we rescale these numbers xij the right way, then they behave the same as eigenvalues of random matrices chosen from the Gaussian unitary ensemble. And so depending on the domain, the weights of the tiling and so on, there have been many proofs and discoveries of such phenomena. So there is GOE, there is also the GOE, so the orthogonal ensemble would show up under certain symmetries. Here are some references and probably others, more recent ones that I have missed. And what is this GOE corners process? So let me just say this briefly. The Gaussian unitary ensemble, these are matrices, Hermitian matrices, such that their real and imaginary part are IID normally distributed variables. And now we are going to look at their the principal submatrices of this matrix. So we have the last one is in this case size 4 by 4. We are going to look at the 3 by 3, 2 by 2, and 1 by 1. And for each matrix, we take the correspondingly many eigenvalues. We list them in an weakly increasing way. Then it's a linear algebra effect that they're going to be real, and they're also going to be interlacing. So they will satisfy these inequalities. So these are the eigenvalues of, in this case, the last matrix, the A4 by 4. These are the eigenvalues of the nested matrix. And the inequalities that they satisfy are these ones. So they're really between each other, just like they are drawn in that pitch. And when we look at the joint distribution, when we are choosing these matrices from the Gaussian unitary ensemble, this is this GOE corners process, or GOEK, that we will denote here. Okay, so how so what other results can we say about this lozenge tiling? So the results in this case for the lozenges near the boundary are the following. So just to avoid the confusion with the x's that were the eigenvalues of the matrices, so we are going to look at the positions of the horizontal lozenges on the kth line. So kth vertical line, so k equals 1 is here, and then k equal 2 is over here, and then we have k equal 3, and we are going to look at the positions of the horizontal lozenges on that line. They are going to be k horizontal lozenges. As we already saw, because of the combinatorics of the model, they are going to be interlacing. And now, if we subtract some number which depends on the shape of the domain that we are looking at, so there's some sort of a mean, and we rescale by square root of n times some other number which depends on the geometry, on the particular geometry, then this collection of random variables, when we are choosing our lozenge tiling uniformly at random from all possible lozenge tilings of whatever kind, this is going to converge to the Gaussian unitary ensemble, k by k matrices. And so in what cases has this been proven? Well, there are many cases that I'm not listing, that I'm missing out, but I will focus on things that I've worked on. Also, so originally it was proven by Kurt Johansson and Eric Nordenstern, and about the tilings of the hexagon. And then if we have this was the region that I was saying was parameterized by the positions of the horizontal lozenges at a vertical line. So say that this is n here, and this is lambda of n. So if lambda n has some limit shape itself, so we lambda n is our parameter, so we are allowed to parameterize it whichever way we want. Then we have this GUE. So the other picture that I was showing when we have vertically symmetric lozenge tiling. So these are vertically symmetric is when we take our hexagon in this case, because it wouldn't really work otherwise. Make the domain. We have over the vertical line. It's symmetric around, or alternatively, we can think of them as lozenges with free boundary, because we are going to look at all possible configurations on that middle line and stop there. And we can also talk about the centrally symmetric lozenge tilings, and we are going to find the same phenomenon. So these were the centrally symmetric, look like this type of symmetry around the center of the hexagon. Of course, the hexagon itself has to satisfy this central symmetry. And so in all these cases, we find this behavior. What else can we say about lozenge tilings using what I'll show in a moment? We can also prove limit shapes. And limit shapes exactly in the sense that Rick Kenyon was saying. So as we rescale the grid, the mesh size goes to 0, then this lozenge tilings, or 3D stack of boxes, they approximate a stepped, they are a stepped surface, and they actually approximate some particular limit shape. So the probability that we get a lozenge tiling that is near this particular limit shape is very high. This is informally the statement, and again, this would hold for all these cases that I showed the GUE earlier. Okay, so let's see how we prove something like this. So let's look at our domain. As I said, we are parameterizing it by the positions of the vertical lozenges on the last line. So here we have big N. And the positions of the vertical lozenges on the last line are given by this partition lambda. And now we are going to ask what is the probability that we see vertical lozenges, horizontal lozenges on some particular vertical line at some particular places. So let's say that if we want at line K to have lozenges at positions, or this would be at the K, at the 1, 2, at this particular positions, what is the probability that we're gonna see this? And now algebraic combinatorics comes to the rescue, because one way to actually see this is with the interpretation through semi-standard Young tableau. I was showing it last time for the growth diagrams with RSK, but here it is again. So we take the first line, we look at the horizontal lozenge that we see here, and it's some number, in this case 3. So we are gonna draw 3 boxes. These are our blue boxes right here, and we're gonna fill them with the numbers 1, 1, 1. Then we are going to look at the next line. So we are going to have 2 lozenges. One is a shifted position 5, and the other one is a shifted position 2. This makes a partition 5, 2. We are gonna draw this partition 5, 2 over here underneath the previous one, and exactly because they are interlacing, the second row of the lower partition is not gonna stick out before the previous one, the one here. So if we fill these numbers with 2, we are satisfying the conditions for semi-standard Young tableau. And then we look at the next position, then the next line has 3 parts, and then we have the numbers 3, 3, 3 in whatever is sticking out. And we can see this on this picture also. So if we have the numbers 1, 1, 1 here, 2, 2, 2, 2, so there is a way. So this would not correspond to any type of height function like this, but there is a way to actually see the tableau on this picture as well. Okay, so now what is the probability that we see horizontal lozenges at some particular position? So if we are going to look at this x k to be equal to eta, it means that the numbers from 1 up to k have to appear in a shape of a semi-standard Young tableau of shape eta. So what is the probability that we see this in this case? Well, we need to have, as I just said, so if we have our shape lambda over here, we are going to have the numbers 1, 2, and so on up to k. So this would be the semi-standard Young tableau corresponding to the first k positions. This will have shape eta. And then the remaining numbers from the semi-standard Young tableau correspondence, because we actually play out this bijection until the end. The numbers in here are from k plus 1 up to n. They form a skew shape, which is lambda minus this eta. And what is the number of semi-standard Young tableau of a given shape without any other restrictions? Is just the evaluation of a Schur function at once. So as we said here, then the number of SS semi-standard Young tableau of whatever shape, skew or straight, with given number of entries is just the value of the Schur function. So we can write this probability of seeing something at the horizontal line as this product, this ratio of products of Schur functions. And now we can form what is called the Schur generating function, which is similar to the moment generating function, except that we replace the monomials in the moment generating functions by these normalized Schur functions, which are also some sort of polynomials. And as we were talking about last time, the Schur functions form a basis. So it's equally good representation in some sense. It's we can still extract some probability from here. So if we take this polynomial, xk is our, so xk is this guy over here. So this is going to be our random variable. And so we sum over all possible configurations. What is the probability that we see xk? Well, we know what this probability is, so we have to do a sum here. And if we do the sum right, then we get the ratio of two Schur functions. And this is this normalized Schur function that I showed in the beginning. Okay, so can we do something with this? Well, when we can actually find this Schur generating function, then maybe we can analyze it, and maybe we can say something about the probability of seeing the lozenge tiling in whatever configuration we are interested in there. Okay, so here is our setup again. Let's say tau n, big tau n is the set of tilings, xj. Again, the horizontal lozenge positions on line j in this case, so from k to j, but whatever. And now, what are these moment generating functions for this the particular set of tilings? So what I was showing earlier was when we were parameterizing by lambda. But if lambda itself has some other properties or can vary through other values, then it's not gonna be the normalized Schur function, might be something more complicated. So this is the previous case. This is from our paper with Vadim. And these other formulas are when we are looking for the symmetric tilings. So these are tilings symmetric about the vertical axis. And in this case, we have this generating function, this Schur generating function, when we have symmetry about the point, centrally symmetric. Okay, so far so good. Okay, so why we have this formula? So the first one I explained quickly. The other two are a little bit more interesting combinatorially and algebraically. But the point for us in this case is that we can do some asymptotics. So how do we prove, for example, the Gaussian unitary ensemble distribution? Well, we can form the same Schur generating function, but this time our random variable is not the positions of the lozenge tilings, it's the eigenvalues of a GOE matrix. It's just mu is just the eigenvalues of a GOE matrix. And then we can compute this to be exactly this. So this is generalized Gaussian moment generating function. Why does this formula hold? Well, you can convince yourself or do the calculation as well, because we have the joint probability distributions for these guys over here, for example. What we also have is that this ratio of Schur functions, this is actually not so hard to compute using this is Weil's determinantal formula. So this would look something like this, and one can actually do the computation even from scratch. And now let's go back to our tiling. So in the region that was parameterized by a lambda, like this, the Schur generating function was this normalized Schur. And now we need to do some asymptotics, and this is how we actually know where the rescaling comes from. So if we plug in these variables, this exponential normalized by square root of n, then we're subtracting something that would correspond to the mean. Then this limit actually converges, and converges exactly to the Schur generating function for the GOE process. So we can state a probabilistic result from this. And of course, the corners process comes from the fact that we have Gibbs conditions, and that would give us the unique distribution in this case. Okay, so this is about the GOE. So this here is gonna come in a moment. I will explain why we can do this asymptotics in a little bit. So just wanted to state another result, that actually this Schur generating function can also be used to do the limit to find the limit surface in some sense. So find not really explicitly as one would wish for, but at least prove the existence in certain cases. And this the setup is exactly the same. So again, we have the same Schur generating function I was showing earlier, and now we will to formalize this measure theoretically. We will talk about this the counting measure given by this normalized numbers corresponding to, in this case, the positions of the lozenges at some certain line, and basically this counting measure, if it converges to some deterministic measure in some sense, then this would actually give us the limit surface. And this is the theory that Alexei Bufetov and Vadim Gorin developed in 2014 and later, is that if there is a particular independence for the Schur generating function, which holds in many cases. So this particular, if we take this particular limit, then we can express it as a sum over, these are independent separate variables. Then if we know one of them, so well, they're all going to be the same because of the symmetry of the Schur functions, and then we can actually extract the deterministic measure to which our counting measures converge. And one thing in terms of lozenge tilings, just to have some idea of what this looks like. So take the vertical line here, we are going to have positions of the lozenges over here. If we take the projection, it's going to look like some partition. And this partition is going to converge to some curve, deterministic curve, when we choose the lozenge tilings uniformly at random. And one can use this approach to study study limit shapes in other cases when we can actually find something explicit about the Schur generating function. So this independence that you see from the theorem, it also follows from the asymptotic that I will show in a moment. But what sort of a result can you get using this?
Sorry, there was
a
question in chat. Dan asks if capital Q from the last slide can be given some large deviation interpretation.
What does large deviation interpretation mean? But basically, so I can tell you what the Q is in this case, because it's going to be the same Q regardless how many variables you take. So in some sense, Q is the moment generating function. Well, it's I would say it's more like, because we're taking these logarithms and whatnot, it's some R transform or whatever was the terminology from free probability, but it's going to be actually the same as the probability, let's say R transform or whatever it corresponds to this lozenge, to the last lozenge tiling here. because we can just take r equal to 1 and it's going to be the same q. So yeah, maybe the answer in some sense to your question is yes.
Yeah, I think that kind of answers my question. I have to think some more, but I think what you're saying is answers it.
Yeah. So okay. So okay, so let's see what we can do for symmetric tilings, for example, using this formalism. So the symmetric tilings in this case are centrally symmetric. Again, picture thanks to Leonid Petrov. And we can prove the limit, the existence of the limit shape using this theorem, and we have a formula in some sense for the moments. So there is this, we have this deterministic measure m, and we can compute the moments for this corresponding to this deterministic measure using some whatever came out of the limits that I was showing earlier, which in this case is this awful function, but it could, if you really want to get dirty, you can actually maybe extract the formula for the limit shape as, you know, actual surface. And the same thing holds for the centrally symmetric tilings. And of course, I should say that, well, because the boundaries and the symmetry conditions hold for the unrestricted case, these are actually the same limit shapes that you would get with without any of these restrictions. Okay, so let me just say briefly how we do this asymptotics. So here is our Schur generating function, and we can do other characters, so orthogonal, symplectic, and just because there is a Val determinantal formula in those cases, but maybe in maybe you can prove something like that even without using the Val determinantal formula. One is this integral representation if we just have one variable. So this is the case k equal to 1. And what we have here is that the normalized Schur function with just one variable, whatever lambda is this complex integral of this rational function here. And x is whatever variable, formal variable we are using in the Schur, in the normalized Schur function. And again, as I was saying, so this one variable case would correspond to just the moment generating function, the original one. So because there is, everything is very simple in this case for the last lozenge. That is next to the boundary. How did we prove this formula? It does come from the Val. It comes from the expansion of the Val determinantal formula, and this integral is just a compact way of writing it as a sum over sum over some partial fractions. So actually, some of rational functions that this integral would actually encapsulate. So if we say that our lambda is approaching some f So our lambda is some partition that is approaching this f after we are rescaling it. So we rescale by n both directions.
Sorry, there is another question about what is the contour?
Oh, for the integral, so inside is the 0, and you can take well, you can take a contour that encompasses all of this, all of the lambdas. Or conversely, you can also do it in reverse, just be around 0.
So there is x to the z, which is not great for z around 0, right?
Right. So the original formula will have these guys. The contour will have all these guys inside, actually. And then when we do the rescaling, we will normalize by n. This will be bounded, so we can actually take the limit in this case. Okay, so if we have this this integral representation, and we can somehow approximate this function at the bottom itself, then we can actually compute the integral using some steepest descent asymptotics, and then we can find approximation for the leading terms of this form over here. So there are two different regimes. So one is the one that this is the LLT regime in some sense, and this is the regime for GUE that we were using. Okay, and the way to actually get the multivariate case from the single variate case is, again, thanks to the symmetry and the determinantal structure of the Schur functions. We have this formula. So we have a van der Monde of this type of operators acting on the product of this single normalized Schur functions that we already can analyze asymptotically. So now, using this in the case where we have only fixed finite number of variables, we can actually analyze this formula asymptotically using the asymptotics for the single variate Schur function, normalized Schur functions, and get some statements like, for example, this is what it was. This was in the condition of Buffetov and Gorin. So this is, for example, the independence condition that would give a LLT. And one can see other. In the GUE case, we still have this type of independence. So,
Greta, you do mean LLN, right? Not LLT. I also know what LLT means, but
sorry, sorry.
I won't say more.
Yeah, so LLT are some polynomials that I've been studying recently, and that's why I'm getting confused. So law of large numbers or the limit shape, yes. Okay, thanks. Okay, so so this is how the asymptotics looks like. And was done, but it's possible to do it. I must say here that John Novak later also obtained these asymptotics results actually in greater generality. So in his case, he could say let K actually vary with n, let's say like square root of n, for example, and still get asymptotic formulas using the Itzhikson-Zuber, the Harish-Chandra-Itzhikson-Zuber integral, and Hurwitz numbering expansions and things like that. So there is not a unique way to see this. Okay, so now I'm going to switch direction to some other, to a similar model, but this time the weights are gonna be multivariate and local. So now we are not looking at the uniformly random lozenge tilings, say of the hexagon or whatever other shape we care about, and this time the weight of a particular lozenge tiling is going to be the product over all the weights for the horizontal lozenges, and the weight for each horizontal lozenge will depend on its position in the tiling, and it's gonna be in general some difference xi minus yj, and if you want to know what xi and yj are, so as we have our 3D lozenge tilings, we actually lay it flat and we put a grid in this direction of x's and y's, and our lozenge tiling is going to have some coordinates in this grid. Now, depending on what the coordinates are, we're gonna give it a weight, in this case given by, for this particular lozenge tiling, it's gonna be x2 minus y3. And in general, if it's a position ij in this grid, then we're gonna have xi minus yj. And here are some simulations of what a typical lozenge tiling would look like. So this is local weights equal to 1. This is the same as our uniform case. And this is the case where xi is n minus I and yj is j minus n, for example. And this is 2n minus I plus j is something. So basically, this is proportional to the distance from the so n in this case is going to be this over here, and a lozenge tiling in this picture. Well, you probably cannot really see this, but it's going to be have weight proportional to its height. So that's why you can see the picture is a little bit more shifted upward. So it's these lozenge tilings are top heavy with this weight. Okay, so why would we look at these particular weights? Because they came out from some interesting combinatorics. So let me just show you some results one can get about them. So now we are going to switch the interpretation slightly. So look at these 3D pictures of the lozenge tilings, but from the point of view of plane partitions. What's a plane partition? This is, well, it's actually not a plane partition, it's a 3D partition, but it's an assignment of integers inside a partition. So maybe this is how it's called. So this is some partition lambda, and then we are in its Young diagram, we are entering the numbers in weakly decreasing order both directions. So this is like the opposite of semi-standard Young tableau, except that now we don't have any strict increase condition, and of course this is making everything much worse in a lot of ways. So we don't have exact any type of exact enumerative formulas for these plane partitions. Well, we have determinantal, of course, but nothing like the hook content formula, for example. And so this is the 3D picture. The 3D picture just says that this tree corresponds to the height of this lozenge over here. This is 3, this is 2, 2, 1. So now, if we are looking at, for example, tilings with height d and base mu, so what does this look like? So base mu is gonna be at the bottom, there is gonna be some shape mu, and the height is going to be d, and then we are gonna look at lozenge tilings parameterized this way. So this is different from what we were showing earlier. And now these lozenge tilings will have particular weights xi minus yj. So here is j, and the weight is xi minus yj. And so the partition function for this is going to be a determinant of with the following nice entries. So of course you will say, oh, there's a lattice path, non-intersecting lattice path is always a determinant. Well, it depends what are the entries of the determinant. So in this case, they are particularly nice. So they're these products. So one can get something like this. And in particular, as a corollary to this theorem, we can recover a formula by Christian Krathenthaler and Stanley and so on from 30 or more years ago about the Q to the volume sum over plane partitions, again, of base mu. So this is our mu base, and now we are stacking boxes on top of this mu of height at most d. And this is, p is just the sum of the numbers or the number of boxes, or basically the volume of this stack of boxes or the plane partition. And then we get this particular determinant, which is so this is q to some power divided by these Pock-HIMR symbols. And here is an example of the case, the very simple case. What are all the plane partitions when mu is 2, 1 and d is 1? So we can have tilings, horizontal lozenges at height 0 or 1. In this case, and there are only so many of them, and this is our generating function. Turns out it's equal to this determinant. And one can ask more questions. So say that, again, we have this weighted lozenge tilings, and I'm not substituting anything for the xi and yj because it depends on what application you want to have. Then using these formulas above, we can talk about tilings of the hexagon and the probability that we have a horizontal line cutting the hexagon like this. So we do not really have formulas for the probability of seeing a particular lozenge at particular place using this technology and this and with nice formulas, but for this we do. And yes, so one can do these simulations, as I showed earlier. And I will say in a moment what these formulas are useful for, and what this model could be useful for towards algebraic combinatorics. So let me just say where this all came from. So it's quite different from what we were talking about earlier. So let's start with a problem. How do we count this number of skew standard Young tableau? So just to remind you, if we have straight shape Young tableau like this one, so we know that the number of Young tableau of this straight shape is this hook length formula, right? Which is really nice, and it enabled Verschicken-Kerov to find the limit shape and so on, the Plancherel limit shape. For skew semi-standard Young tableau, or for skew standard Young tableau, we do not have this product formula. And you can convince yourself that you probably are not going to find it. Why? So first, what formulas are there? Well, there is the determinantal formula, just because, again, there is a non-intersecting lattice path interpretation, and one can actually extract this determinantal formula out of this. There is, if we want something positive, we can write it in terms of Littlewood-Richardson numbers, the Littlewood-Richardson coefficients, but they themselves don't have nice formulas, or asymptotics for that matter, which is going to be a topic of tomorrow's lecture. There's already a major problem. So, and you can convince yourself this is not going to be so nice, because we can take this staircase shape, zigzag shape, and so this would be the skew shape between two staircases of thickness 1 and thickness 2. What are the standard Young tableau corresponding to this shape? Well, if we read the numbers along this zigzag path over here, we are getting an alternating permutation, increasing, decreasing, increasing, decreasing. So and what's the number of alternating permutation? These are the Euler numbers. And what's their generating function? Well, it's this one. Well, we have some transcendental function, so we cannot really hope for some very nice formula here. Okay, so what other formulas are there for counting skew standard Young tableau? Well, there's a more recent one which came from algebraic geometry, actually, and this is formula by Keda and Naruse, presented first at the SLC in 2014. Number of standard Young tableau of shape lambda over mu is something like a hook length formula, except that now we have sum over several types of diagrams, and when I say several, I mean a lot. But still, it's a positive sum. What are these excited E of lambda slash mu? These are the excited diagrams. So the idea is that we have lambda over here, we have mu over here, and we start moving the boxes of mu. We slide them along their diagonals so that they cannot really overpass each other. So just imagine that they are actually solid, and they are respecting the laws of traffic along these lines. So here is one way to get an excited diagram. So we take this, this is mu over here. So we can move this box over here, then we can move the next one over here, and this one over here. There is nothing in the way preventing this. So this is one example of a excited diagram. And what are the hook lengths? Are the same way we measure hook lengths in the original formula, except we only look at the white boxes, so not the boxes that came from mu, and we And the hook lengths are going to be exactly, so these numbers are the hook lengths of this box inside lambda. So here is 5 and 6 and so on. And so here is an example from the previous case when we were looking at these alternating permutations. In this case, we have 5 excited diagrams, and each of them is contributing these terms in the formula. And one can generalize this, so we can take a Schur function, evaluate it with the principal specialization powers of Q, but it's only infinite in this case, and we have the same, the Q analog of the original formula holds, so we're summing over these excited diagrams, and we have these rational functions, which are really something like a Q analog for the hook lengths. And here is an example. If we take the Schur function of this shape, skew shape 3, 2, minus 1, so this is this particular shape over here. And if we write it out as a sum of powers of Q, of course, these are going to be the contributing terms, and there are many more, and it's, of course, an infinite series. And a similar formula holds for the plane partitions. In this case, the way we phrased it is in terms of reverse plane partition, but because we have this freedom of choosing lambda over mu, we can also do normal plane partitions of the opposite shape if we want. So this is lambda, this is mu, and what's a reverse plane partition is an assignment of the numbers inside the boxes of lambda over mu, so that they are weakly increasing along rows and down columns. And again, because we don't have the strict condition and we're losing the semi-standard Young tableau, things become much worse. And now we are going to sum over other diagrams which contain the excited diagrams in themselves, and we'll have the similar geometric expansion over here. So here below is the example of reverse plane partition of this shape. So they're more than the semi-standard Young tableau. And how do we prove this? Well, the original proof or algebraic proof comes from equivariant Schubert calculus, localization of Schubert classes, Grassmannian permutations, and this can be expressed as evaluations Schubert polynomials, and which in this case are factorial Schur functions. Factorial Schur functions are certain parameterized generalization of usual Schur functions. Maybe we'll see this in a moment. We also found a bijective proof using a generalized version of RSK from this Q semi-standard Young tableau, characterizing basically what sort of our integer arrays exactly are producing these ones. And another proof is using non-intersecting lattice paths, and because we are in integrable probability, we like lattice paths, especially if they're non-intersecting. I'm going to show you this proof over here. So, well, okay, we are using a formula, which I don't really know if one can prove this formula using non-intersecting lattice paths, but it's a generalization in some sense of the Jacobi-Trudi identity, or the Giambelli formula that was mentioned last time. We any Schur function can be written as a determinant of ribbon Schur functions, and the ribbons are determined by the shapes that we are cutting. We are cutting from the skew shape, and the endpoints are as drawn over here. So basically, we cut out the outer border as a ribbon, then we cut out the next one until we cannot cut out anymore. So here, for example, we had to stop because mu stopped us, and then there is this other guy. And when we have the the outer shape lambda, this is basically telling us what kind of path between, what kind of ribbon we can have between two endpoints. So this is the Schur-Pragas or Hamel-Golden identity. Is giving it as such a determinant. And so let's apply this formula. So we need a formula for Schur functions with which are border strips shape, like in this case. So thickness 1 box. This is our theta. And when we specialize 1q, q squared, and so on, we are getting that this is a sum over all possible paths from the two endpoints. So these are the endpoints over here. Say this is AB and this is CD, and they are inside lambda. And for each of this path, we have this hook length analog. This is exactly what we want in as a weight in the Narusse hook length formula. So local weights on the paths, this is important. And here is an example. If we take lambda to be 332, and these are the endpoints. So these are all the possible paths that we get here, and these are the contributions from each one of them. And one can prove such an identity by induction or some more. There are more algebraic tools as well. And now let's put everything together. So one thing to see is that these excited diagrams, if we look at their complement and we cut it, but this time by the inner border. So first we cut the top inner border from the skew shape, and then whatever is left, we get another ribbon and so on. So we can cut our skew shape into lattice paths in this way. And every time we make an excited move, that we are basically changing the lattice path to pass above that box. So we are changing corners in the lattice path, and when we do all these excited moves, we get all possible non-intersecting lattice path configurations with these endpoints that were fixed by cutting originally. And so this is really what these excited diagrams are. And now let's put everything together. So the Schur function using Schur-Pragas is this determinant of ribbon Schur functions. Now we use this formula for the Schur function and border strips, and this formula is really sum over all possible lattice paths with whatever endpoints we had fixed inside lambda. So we have these lattice paths, and then of course we have a determinant of these things that, as you can see here, have the all possible pairs of endpoints for the lattice, and each entry is just sum over all possible lattice paths between 2 points. So now we can apply in reverse the non-intersecting lattice path formula and just cancel out everything that has intersection. So we are going to get that we're summing over non-intersecting lattice paths with this particular weight, and this is exactly the weight that was coming into the Narusse hook length formula. And the lattice paths correspond to excited diagrams, as we just said over here. So we get this particular formula. So for the multivariate case, these are the factorial Schur functions. And so it's a specialization. So in this case, we have a formula exactly because these things originally came from this equivariant Schubert calculus, as I mentioned. So we have a formula which says that we sum over these excited diagrams of things that look like this. So these are certain parameterization, and these are actually the permutations that are the Grassmannian permutation, but we're not really going to go into that right now. And then we get a factorial Schur function, and a factorial Schur function has a certain determinantal formula definition similar to Weyl's determinantal formula, but with parameters. So we have a formula like this, and this is how we got the other determinantal formulas. And this is again a simulation, now different shapes, and again it's you can see the difference between the two types of weights. So in one case, these are really the hook weights, the other ones are the uniform. And just to say one word about applications, so we can use this this Narusse-Cook length formula and lozenge tilings in reverse, in the sense that we can get some information about the asymptotics for the number of standard Young tableau of skew shape. And so you can get at least some leading term asymptotics for in various domains. What Alejandro, Igor, and Martin did was that they used a variational principle, the same one that Rick was talking about, using a variational principle for the multivariate weighted lozenge tilings, and the Narusse-Cook length formula to get their number, and their number, the asymptotics for their number, and the number is of course the number of standard Young tableau because of this formula. So you can use this in reverse. Of course, the variational problem does not let you determine what the next term in the expansion is going to be so easily. So this is still in various cases open problems. But there are still many other questions that we would be interested in. And next time I will talk about asymptotic algebraic combinatorics with many open problems, and hopefully some of them solvable using using integrable or maybe not integrable probability. So I hope you'll do some of that. So thank you very much.
Are there any questions apart from the ones that were already asked?
Greta, so the last stuff you were just talking about, the asymptotics of skew, Schur polynomials, have people used this to kind of interrogate the limit shapes or large deviations of limit shapes of tiling models?
So this is something I wanted to do in some, but this we still don't have good asymptotic formulas for skew Schur functions. Unfortunately, nothing of the kind that we did with Vadim, nor does this Narusse-Cook length formula help with that case so far. So still an open problem, but it could be used just with the usual Schur generating function. You can do more general domains if we could do asymptotics of skew Schur functions.
Okay.
I have a little question. So Naruse formula, it starts from having from a determinant, then you rewrite it as a positive sum, right?
Mm-hmm.
Which is pretty much like, well, non-intersecting lattice paths principle, right? The determinant is a positive sum. So
Well, it depends which determinant you start from, because the thing is that if we start from Jacobi-Trudi, the interpretation is not gonna be very useful. It's not gonna give you the terms in the Naruse-Hook-Lane formula, right?
yeah, sure.
Yeah. So so the benefit of the Naruse-Hook-Lane formula is that it's actually compact in some sense. So these excited diagrams, there are finitely many, especially. They're independent of other parameters in the picture. So, and this is how we also did the asymptotics. So depending on what regime we are, there are less excited diagrams than the contribution from each of them, for example, and things like that.
Right. Thank you. Do we have any other questions?
Actually, building on that question, so I guess you already thought about this. Can you do anything if you start from the Jacobi-Trudi? Do you know any asymptotic, even in one variable, maybe it's
Yeah.
not interesting, but
Yeah. Nothing good, honestly. So actually tomorrow, if I have time, I'll talk about some very recent application of Naruse-Hook-Lane formula for even finite length Young diagrams, where using Jacobi-Trudi, you can still not get anything out of it. Somehow it's the problem with Jacobi-Trudi is that when you do the leading terms asymptotics from each contribution, they cancel out in the determinant. So you really need to be very careful. Somehow, yeah.
And I guess if we're here, what about Jambelli? Or I can go on.
Sure, I don't know. In my view, it would be isomorphic.
No, the reason I'm asking this is because when you do these fermionic models, it's really the Jacobi-Trudi and in some sense the Jambelli that come out naturally, and never the Weil formula. So
Yeah,
you know,
because
Verchetik in Schur processes and whatnot, all of those.
Yeah, but the Weil formula is very special already. So the lattice path interpretation holds in greater generality then.
Yeah.
So yeah, I don't know. I myself have not been able to get something useful out of this determinant, but it should be possible in principle. So.
Okay. If there are no more questions, last chance. Let's thank Greta again.
Okay, so I'll close out this session and start a new one. We'll resume in, I guess, 20 minutes or so with, I guess it's Rick is giving his talk. All right, so I'll see you all in a little. Bye.
Thank you.